Here's a quick example of using the normal approximation to the binomial probability model. Very practical example of overbooking on an airplane. So suppose that on average, or typically, 10% of airline passengers fail to show up for their flight. Or maybe for this particular flight on this particular airline, they've observed that 10% of airline passengers fail to show up. So they've got a 280-seat airplane. They could just sell 280 tickets, but then they probably have on average a 10% empty airplane. That seems like wasted money from the perspective of the airline. What if they book 300 tickets? They get more money, and probably not all those people are going to show up. In fact, our expected value of the number of people coming for the actually getting on the airplane, expected value of people showing up. Hey, that's a binomial problem. We've got hopefully independent people. Now that's not necessarily true. What if there's like a soccer team or something of 50 people that all come together? That would mess this up. But let's assume they're all independent. Equal probability of 90% showing up. That's 1 minus the 10%. Then expected value is just NP. So the mu equals NP is going to be 300 times 0.90 is 270. So on average, we would expect actually still to have some empty seats. What's the probability, though, that we actually overfill the airplane? And the bad side of that is they have to kick people off and usually have to give people some sort of premium, like a free ticket or a voucher, which we'd rather not have to do. It's not the most horrible thing in the world, but we'd rather not have to do it. But we'd like to know what's the likelihood that we'd have to do that. Okay, so we want the probability of x. Let's say that's our random variable of number of people showing up. Let's go ahead and do that. X equals number showing up. We want the probability of x is greater than 280. Okay. Well, so that's not usually how, if we're going to translate this into a normal model, that's not usually how it works. That's going to be 1 minus, though. Let's see. We don't really need math mode yet. That's 1 minus the probability of x is less than, let's see, it's going to be less than 281. Okay, so if it's greater than 280, it's anything up to 280, so that's less than 281. Now, we're going to explore the difference, like, does it make sense to say 280 or 281, the less than, or equal to? At the end, we'll quickly discuss the import of that, and the answer is going to be it doesn't matter very much. Okay, alrighty, so that's going to be approximately equal to 1 minus the probability, now suddenly I'm in math mode, woo, of, let's call it y is less than 281, where y is a random variable with a normal model that approximates x. Okay, and how do we find that? Well, what we know is that the mean of our x, that was equal to mu, we know that's 270. Okay, we also know that the standard deviation of x, that's discussed in a math box. I haven't made a video about it yet, but I might. That's our sigma, is equal to the square root of NPQ. Alrighty, that's the square root of 300 trials, and then times 0.90 times 0.1, and that's equal to about 5.2. Okay, so if it's true, and I did another video hopefully convincing you with some examples that this really is true, that when you've got large numbers, that the binomial model is approximated well by the normal, then it should be a normal with this mean and this standard deviation. And that's all you need to describe a normal. Okay. Let's check, though. Check the condition to see if it really is likely to be close to normal. NP is 300 times 0.90. Okay, that's the 270 that we got already. That's definitely, the expected number of successes is way bigger than 10. And the other thing you have to check is the expected number of failures. NQ. But that's equal to 300 times 0.10. And that's 30. That's also greater than 10. There's various different rules of thumb in the literature, but this is a pretty conservative one that our book suggests. If NP is greater than 10 and Q is greater than 10, we're pretty darn sure that it's a normal is a pretty decent approximation. Okay, so we're good. And now we just need to use the normal distribution. So the probability of a normal being less than 281, okay, that's by definition, that's just the normal CDF of a, let's say minus 1,000 or something like that, to 281 with a mean of 270 and a standard deviation of 5.1962. Okay, and that is equal to, do that on the calculator here, and I didn't want to start up the document camera so you won't be able to see this, but we've done this before. 5.2962. The 2962, you don't really need all this accuracy here. It's not going to affect things very much. Okay, is 0.981, or 98.1%. Now remember what that was. That was the probability that it's not overbooked. And so the probability that our variable is greater than 280 is approximately equal to 1.9%. So only less than one time out of 50 with this scheme are they likely to overbook the aircraft. Okay. Now let's look real closely at should we use 281 or 280 or less than or equal to? The normal distribution is a continuous distribution, so it would actually make sense for this to be 280.9, 281.4, 281.5, 280.5, and there's various different opinions about exactly how you choose this. And the main thing is when the numbers are big enough so that these approximations are good, it's not going to make a big difference. Okay, so for example, if we look at this normal CDF and we change it to 280, just to play with that and say, would that make a difference if we change that? Then I'm going to do that real quick on the calculator. It turns out to be not a huge difference. It's something of a difference in this case, 0.97. Okay, so instead of 2%, it's going to be about 3%. So it can make something of a difference, but it's never going to be drastic in the cases that we're looking at. And so our book tends not to worry about that. When they have a footnote about the continuity correction, that's what they're referring to, is the difference between these kinds of answers. So I'm not going to make a big deal out of it unless we find a situation where we really want to be very, very precise. So this kind of answer would be fine for us. 98.1% of the time it's not overbooked, and so about 1.9% of the time it is overbooked. All right.